Okay. Good morning. Today we're going to topic we're going to cover is known as longitudinal shear. I did a bit of intro on Friday, and I'd like to recap that. So in longitudinal shear, the loading is based on the strength of the joint. And I showed to all of you wherever or in a structure where the structure will fail first is at the where? At the joint. Okay, so failure will always occur at the joint. Then there's a new formula that we have to learn. Okay, it's not so much difficult. It's failure will occur at the joint, and the shear flow Q is equal to fastener resistance force divided by fastener resistance or fastener space. Now we have to include two more rules on longitudinal shear. Okay, and one of it, the members must entirely distribute the shear stress. Then this is followed by the joint of fastener is to transmit the shear stress or shear flow from one member to the other. Okay, so this is basically the theory, but there are some cases where I'll show you some examples that the analysis is not so straightforward, but it is not impossible for you to handle if you apply all the rules that we have learned. Right, so I'm going to go through an example and I'm going to lecture together with the example, okay? So this example has been posted on Friday. If you look at your Friday notes, you will see it. I'm going to put this over here. And this is the sort of question that you will get, okay, as an engineer. You're given these values, but they don't tell you what it's used for. Right. The double wedge griddle is constructed from two plywood sheets that are secured to the wood member at its top and the bottom. So we know the whole structure is made of wood. Okay, we know the whole structure is made of wood. Thank God, not sandwich material. Even if it's sandwich material, all of you are able to handle it. Yes or no? Okay. Now, what is given to us is the allowable bending stress for the wood is 8 KSI. Then the allowable shear stress is 3 KSI. If the fastener are spaced 6 inches and each fastener can support 600 pounds in single shear, determine the maximum load P that can be applied to the beam. So what we are going to do is we're going to determine the value of P. Okay. Now, before I go on, okay, let's look at the question. This has a lot of layers. Okay, so what do I mean by layers? First given to us is stress allowable, normal stress allowable. Is equal to what? Is equal to 8 times 10 to the power 3 PSI. So it gives us a sense that failure can be due to what? Normal stress. So this is for normal stress failure condition. The next thing that comes to your mind, what formula we're going to use? Yes or no? Okay, we are given normal stress, what formula we're going to use? Formula, if we're going to label this as our transformation, this is X and this is Y. And over here, what it shows us is the cross-sectional view. So when that's the case, this is our V, our Y, and this is our Z. So we know we are given that the normal stress allowable is 8 times 10 to the power 3 PSI. So this is the normal, is for the normal stress failure condition. So the formula that we're going to use is stress X is equal to Px over A plus or minus My over Iyy multiplied by Z plus or minus Mz over Izz multiplied by Y. Okay. To our blessing, there's no normal stress. There's no axial. So this is due to what? This is due to axial load. To our blessing, there's no normal load over here. Okay, so this you can cancel out. Then the next thing we know that over here, this is our rotation about Z. Okay, so there's no moment about Y. So this is equal to 0. This is only the formula that is standing. Be clear. So this is one condition. So this condition, normal stress failure condition due to what? Bending moment. Then the next thing comes is they give us shear allowable is equal to VQ over IT. Okay. So we know this, not VQ, sorry. The shear stress allowable is equal to 3 times 10 to the power 3. Okay, 10 times 10 to the power 3 PSI. Okay. So from here, we know that we are going to find the shear stress or the shear failure okay, shear stress failure condition due to what? Due to shear force. Okay, due to shear force. So we know that the formula that we have to use, the shear, is equal to Vy over Izz Qz divided by T. Okay. So that's the second failure condition. Now this will occur at the where? At the centroid. Yes or no? Right? This will occur at Y max. Okay. So none of this seriously address the joint yet. Yes or no? Right? None of this address the joint yet. So what we are given is that failure. The next one we're going to look at is failure due to the joint. Okay, I'm going to get the image down here. Now, I'm not just doing an example, I'm also lecturing at the same time, okay? So failure at the joint. Okay, we look at the failure at the joint. And we know this is related to shear flow Q is equal to VQ over I. And this is also equal to what? Equal to the resistance, fastener resistance force. And then we are going to divide by its spacing. Now, both of these can be equal because if you look at the units, this is Newton meter cube per meter 4. This is equal to Newton per meter. So spacing of fastener, I beg your pardon. Okay, so when you cancel here, the units are the same. Okay, so we are given that the fastener resistance force is equal to what? Is equal to 600. Okay, 600. 600 Newton. And we are also given the spacing of fastener, which is equal to spacing of fastener, which is equal to what? 6 inches. Sorry, pound force. I do beg your pardon. Okay. Oh, so this is I can't remember. 6 inches. If I change this to imperial units, okay, so this is pound inch to the power 3 over inch. Is this in inches? Oh yeah, it's in inches. Inch to the power 4. This will be equal to inch, pound, inch. You cancel, you cancel the same. Okay. So these are the information we are given. Okay. Now, a question for all of you. How is this related to shearing? How is the fastener resistance force related to shearing? Okay. Only if I can convince you that, then you will want to calculate the what? Shear flow. If I don't convince you, you say, why is that? Okay. So first question, how did they get 600 pounds? And 600 pounds is dependent on what? Don't look at this. How many of you have built that? Good. Good. Okay. If the nail is bigger in diameter, it's more difficult to nail it in. Yes or no? Right? If the nail is longer, what happens? Yeah? It's harder. So the first time you knock it down, it's easy. Right? Let's say you have a nail this long. The deeper you nail it in, what happens? You need more force or less force? More force. Remember this. Okay, I'm going to bring in the theory and then go bonkers. Let's remember this. The bigger the diameter, more. The longer the length, the more force there is to what? Right. More difficult means more resistance to what? Force. Okay. Now, a question for you. Then how do we determine the fastener resistance force? Very easy. You know, mechanical engineers will take forever to make beer. Chemical engineers are quicker at making beer. Any idea why? Anyone? Because of they do. They do experiment. So now my question to you, how do they determine 600 pounds? By what? Don't think so complicated. Every mechanical engineers, when we make beer, what do we do? We buy a book to learn how to make beer. The water has to be bubbling. The hop has to be from South Africa. You go crazy. What do chemical engineers do? They just buy everything and start making their beer. And the first time they make the beer, how does the beer taste? Tastes like shit. Thank you. Then after that, what do? They do what? So as mechanical engineer, adopt the same. They go just think, then nothing happens. Nobody moves, nobody dies. Okay. Now the thing is this. I'm going to now sketch how we plug the nail and what are the forces associated with it. Okay. So now we look at the nail now. So this is determined by experiment. Now, those of you who have built a deck before, what determines the spacing in between the nails? I'm going to teach you that. If you're going to put a grand piano on your deck, you have to make sure the nails are closer together. Are we clear?